Okay, in this video we're going to introduce Legendre polynomials. So we're going to go through some basic definitions, etc. So, well, Legendre polynomials belong in a class of the so-called orthogonal polynomials. We'll see what orthogonal means as we go along. So these polynomials belong in the class of orthogonal polynomials. So in this class, they are not the other polynomials, but orthogonal polynomials typically arise as solutions of some standard ODEs and PDEs. So these arise as solutions of some standard linear ODEs and PDEs, typically of second order. So I'm just going to list some of the applications of orthogonal polynomials. So we mentioned that these polynomials have numerous applications, including the following. So we've already said that they arise as solutions of ODEs and PDEs. So just like I think at this point we've encountered say sines and cosines and exponential functions, and we know that there's some standard there's okay as a solution to some standard ODEs. These polynomials are also used in numerical analysis. So this is basically in the solving of ODEs and PDEs numerically. So they are typically used there to represent functions. They are also applicable in probability theory, and of course they're applicable in mathematical physics. We're just going to list some of the classical orthogonal functions. So the following is a list of the classical orthogonal polynomials. I'm going to list them in alphabetical order. So there is the Chebyshev polynomials. We have Hermite polynomials. we have Legendre polynomials, and of course we have Legendre polynomials, which we'll study. Here we have Jacobi polynomials, we have hypergeometric polynomials. Okay, so we're going to end there with that list. Now, so as we've said, these polynomials, Legendre polynomials, typically arise in the solution of problems involving spherical symmetry. So these ones arise in the solution of problems involving spherical symmetry. So in this context, they are going to be solutions as solutions of the following ODE. So 1 minus x squared y double prime minus 2xy plus n into n plus 1y equal to 0, where n is an integer. So this ODE here is called the Legendre differential equation. So they can be defined using this equation. Let's list two alternative ways of defining Legendre polynomials. So definitions here. There is what is called the generating function. So the generating function g of x h of the Legendre polynomial is 1 over the square root of 1 minus 2xh plus h squared. So this is equal to the summation of h to the power n times Pn of x. So by the way, the notation for the Legendre polynomial is P sub n, where n is the degree of the polynomial. So what this equation is saying is that if we expand this expression in powers of h, then the coefficient of h to the power n is going to be the nth degree Legendre polynomial. We will show how this works in a moment. There is something else called Rawricks formula. So Rawricks formula. So Rawricks formula expresses or defines the Legendre polynomial in a differential using a differential formula. So this one says the nth degree Legendre polynomial is 1 over 2 to the power n factorial times the nth degree derivative of x squared minus 1. So here, if you want the second degree polynomial, for instance, then it's going to be 1 over 2 squared times 2 factorial. Then this is going to be the second order derivative of x squared minus 1 to the power 2. All right, for now though, we're going to go back to the generating function here, and we are going to show you how we derive the first, say, 3 Legendre polynomials. So what we're going to do is we are going to expand g of xh in powers of h using the binomial theorem. So we're going to note that this is not the only way of doing this. So this is going to yield our Legendre polynomials. So what we're going to do is we are going to expand up to h squared. So we demonstrate by expanding up to h squared. Okay, so g of xh is 1 over square root. So what we're going to do is so it's 1 over square root 1 minus 2xh plus h squared. So we're going to rearrange this, and we're going to write it as 1 plus h squared minus 2xh to the power negative 1/2. So this is going to be our first term, this is going to be our second term. So using the binomial theorem, so the first term is going to be simply 1. Then the second term is going to be minus half, which is this minus half here, h squared minus 2xh. Then the next term is going to be minus half times minus 3/2 over 2. Then we're going to have h squared here minus 2xh squared. So we're going to have 1 minus a half h squared plus xh, because the 1/2 times 2 there is going to cancel out. And then if you're only interested in terms up to h squared, the only h squared term from here is going to be the last term of this expansion here, which is going to be 4x squared h squared. The other terms are going to be higher degree, like h to the power 4 and h cubed. So this is going to be 3 over 8 from here. Then from here we're going to have 4x squared h squared. Then we collect terms, so the only constant is going to be this one. The only term involving h to the power 1 is going to be that one. And then these two terms are going to be the terms involving h squared. So this is going to work out to 3 over 2h squared, and this one is minus a half. Okay, so from this we this tells us, let me just do this. Just going to write these So this is the same as h to the power 0, then h here, then h squared. So the coefficient of h power of h gives us the polynomial of degree same as the power of h. So that means p naught is going to be 1 from this term. P1 is going to be x from this term, and P2 is going to be 1/2 into 3x minus 1. We're going to see graphs of these in a moment. So yeah, there you go. So let's just mention here that the same result can be obtained, so alternatively these polynomials can be derived by expanding the generating function in powers of h again, but this time via the Maclaurin series. Okay, via the Maclaurin series. So it's going to be a good exercise for you to go through this process and indeed confirm that we get the same result as this. So if again in that process you just work things out up to h squared, then that would be good enough for now. Right, the last thing we're going to make note of before we look at the graphs of these functions, which we should already have a picture of actually, because this is just y equals 1. This is x, which is a straight line, and this is a parabola. The next one is going to be a cubic. So in this course, we are going to study the Legendre polynomial. However, we will be expecting that from our study you can work with any of these other polynomials. Indeed, in our exercises, we've got exercises on, say, the Hermite polynomials, etc. The reason for this is that the structure of these polynomials is the same for all of them. So once you have seen one, basically you've seen all of them. So for instance, the Hermite polynomials will have their own generating function. They will have a corresponding differential equation. They'll have a corresponding Rawricks equation, etc. All that happens is that for the other polynomial, this function, for instance, is just going to be different. So it's just algebraic differences. Otherwise, in terms of the qualitative features, all of these polynomials are going to have the same structure. Okay, so we're now going to look at the graphs of these. Typically they are defined and useful in the interval -1 to 1, and then after that I think that's going to bring us to the end of this video. All right, so here is the graph of these polynomials here. So the red one at the top here, this one, this is your Legendre polynomial of degree 0. Remember, that one is equal to 1. Then the Legendre polynomial of degree 1 is the green one here. So remember, P1 is equal to x. So you can see it's just a straight line through the origin with gradient 1. Then the orange one here, this one is going to be the second order, which we worked out to be 1/2 3x squared minus 1. Okay, then this one is going to be the blue one, is going to be the Legendre polynomial of degree 3. It is going to be a cubic. And then the purple one here is going to be the Legendre polynomial of degree 4. Again, it's going to be a fourth degree polynomial. All right, so I think we're going to end it here in terms of our introduction to Legendre polynomials. In the next video, we're going to start looking at some of the properties of Legendre polynomials. Thank you for watching. Please do subscribe so that you can get notified when we post new stuff. And indeed, if you have questions or comments, we will appreciate if you post them under the comments section. Thank you.